Okay, let's go now to the second video, and in this video we will understand the significance of correcting for multiple tests. So typically in microarray experiments, in general in biological experiments, we make a test. Here in the expression analysis we make t-test for thousands of genes. Which means that we apply a statistical procedure not in one comparison, not for one gene, but for thousands of them. Now, for every such a test, what we do is that we set a significance threshold alpha, which is usually 0.05, and then we perform the t-test and we find a p-value. So the order is like that: t-test and then a p-value. So the null hypothesis in this test is that in the two categories, let's say healthy people and disease and sick people, the mean expression value is the same between them. So this is the null hypothesis. Perhaps the alternative one is that the expression level in the healthy people is greater than in the disease people, but there are other alternatives as well, like this one or this one. Okay, in any case, we set a significance threshold alpha, 0.05, we perform a t-test and we find the p-value. So if the p-value is smaller than 0.05, we reject the null hypothesis and we accept the fact that depending on the alternative, that for example the mean expression value in the healthy people is greater than the sick people. If the p-value is greater than 0.05, then we cannot reject the null hypothesis. Be careful here, because statisticians do not like saying that we accept the null. So we never use this word accept. We just say that we cannot reject the null hypothesis. Okay. So if the p-value is smaller than 0.05, then we reject the null hypothesis. If the p-value is greater than 0.05, than the significance threshold, then we cannot reject the null hypothesis. Now, why we set this alpha here is because is in an effort, what we try to achieve with this alpha here is to control the false positive rate. So just to remind you here that the false positive is when the test says that the test rejects the null hypothesis. So the test says that there is significance difference between health and disease, but in reality but in reality there is no difference. So the false positive rate is when we reject the null, when we should not reject it. If you remember the simulation that we did in the previous video, then we had created an example of 10,000 genes. The expression level of these genes in two populations, health and disease, are all coming from the same distribution, same normal distribution with mean 100 and standard deviation 10. And we saw that in several genes, around 500 of these genes, so these genes that have a p-value less than 0.05, we could actually reject the null hypothesis. Even though we should not reject it because all these genes are coming, the expression level of all these genes has exactly the same mean value. It's coming from a population of exactly the same mean value of 100. So the null hypothesis is correct for all these 10,000 genes here. It's correct because both the healthy people and the sick people are coming from a population that has a 100 as the mean value. Okay, so whatever rejection we do here, it is a false positive. It is false because we should not reject the null, and it's positive because the test says that we should reject the null, but we should not do it because in reality the null hypothesis is correct. Okay, so the reason that we set such a small value as the significance level here, significance cutoff value, is because we want to say that even if the null is correct, even when the null is correct, is true, then the probability to find a p-value that is smaller than alpha is alpha. So if this is 0.05, this will be 0.05. So when the null is true, then the probability to find a p-value that is smaller than 0.05 is exactly 0.05. And since this is not a very high probability, we take the risk to reject the null hypothesis. Now the problem comes when we have to do multiple hypothesis testing. Whatever we said before with 0.05 is okay if we do just a single test. However, when we have to do multiple tests, we have the following problem. First, we must introduce the term family-wise error rate, or which is the probability to make at least one type 1 error, as called, or at least one false positive. the same. So at least one time to reject the null while we should not do it, while the null is correct. So this probability here is called family-wise error rate. Now, if the null is correct, then the probability to make a type 1 error rate, so to reject the null hypothesis even if we should not because it's correct, it's alpha. So the probability to not make a type 1 error is 1 minus alpha. So this is of not making a type 1 error, which is a probability to not reject the null hypothesis when we should not reject it, when it's correct. Okay, now if we perform two experiments, the probability to make a type 1 error in none of these two experiments is, and these two experiments are independent, will be 1 minus alpha for the first experiment multiplied by 1 minus alpha for the second experiment, which will be 1 minus alpha squared. If we do m experiments, then this probability of not making a type 1 error in any of them, m experiments, will be 1 minus alpha to the m. So the probability to make, so this is the probability to make no type 1 error in none of the m independent tests that we had. Again, type 1 error means to have a false positive, so to have a positive result, to find differential gene expression, for example, to find that the genes are different between the two classes when actually there is no difference between the two classes, so it's a false positive. Okay, therefore the probability to make at least one type 1 error in these m experiments is 1 minus alpha to the m. Now if we make the graph of this equation here as a factor of m, as a function of m, so m is the number of experiments, we will see that we see the following. If this is 1, so if we make one experiment, then this will be 0.05. It will be the same like alpha. And here is 1. So this increases like that. Does not reach 1 exactly, but it goes very close to 1 as m is going larger, which means that more or less for sure we will make a type 1 error when we perform multiple tests. Now, let's call this quantity here, let's call this quantity alpha prime. So alpha prime is 1 minus 1 minus alpha to the m, and this quantity is the family-wise error rate. So the probability to make at least one false discovery when we should not do it. Now there is a mathematical equation that says that this is smaller or equal to this alpha multiplied by m. So as an example, if m equals 6, then and alpha equals 0.05, then this number, if I remember well, it's something like 0.26 or something like that. So this is the alpha prime, while this quantity here will be 0.05 multiplied by 6, which could be 0.3. So definitely this is greater than this value here. Therefore, a way to correct for this false, to correct for the false positive rate, so to control somehow, okay, the question now is how to control the false positive rate when we perform multiple experiments. And this is an important question because in biology usually we perform multiple experiments. So for example, when we compare the gene expression level, we compare it to thousands of genes. So these are a lot of experiments. Okay. So let's suppose that we do m experiments, and the family-wise error rate has this relationship here with the significance level for one experiment. So this is for one experiment. And this relationship here with alpha and m. Now, if we set as alpha per experiment a value that will not be 0.05, but will be, for example, 0.05 divided by m, then we will have that alpha per experiment, I will just write it like that, multiplied by m will be 0.05 divided by m multiplied by m. So I just apply this here, which will be greater, based on this inequality here, to the alpha prime. So if instead of using a significance threshold 0.05 per gene, we use a much smaller significance threshold for a single experiment, and this much smaller will be 0.05 divided by m, then we can control the family-wise error rate. Okay, let's see this, how it works in practice. So again, we have this matrix that comprises 10 individuals, 5 from a healthy population and 5 from a diseased population, and all of the values, all the expression values are coming from the same distribution, which means that the null hypothesis is correct. So whatever we'll find now will be a false positive because the null hypothesis is correct. We have the t-test. Now, if we set as a threshold, as we said, the alpha 0.05 divided by the number of experiments, remember that here we had 10,000 genes here, so we have 10,000 experiments, then what we will find will be 0, like 0 genes, 0 comparisons reported as positive, so 0 times we rejected the null hypothesis, which is good because this dataset, in this dataset, the null hypothesis is correct by definition, by construction of the dataset. So we did not reject the null hypothesis in none of them, and this is good, this is fine. Now the problem comes, so another way to see that is the following. Instead of setting as a significance threshold now this 0.05 divided by 10,000, what we can do, so we say that we'll reject now the null hypothesis. Okay, let's put that properly here. We have done m experiments, and we write that we will reject the null hypothesis if the p-value of an experiment is smaller than 0.05, which is the alpha, divided by m, which usually is 10,000. So it's 10,000 in our case. So in our case, m is 10,000. Now this is the same as writing that p-value multiplied by m will be smaller than 0.05. So this thing here is the corrected p-value. But since we want this to be something like a probability, so this to be a number between 0 and 1, this multiplication here does not guarantee that this number will be between 0 and 1. For example, if a p-value is 0.001 and m is 10,000, then this number will be 10. And we usually don't like to report it as corrected p-value because p-value should be a probability, so it should be a number between 0 and 1. And therefore, if this multiplication will give a number that is greater than 1, we'll just report 1. Okay, in R, the function that we use to correct the p-values and get a number like that is the function p-adjust. And this method that we just multiply the p-value with the number of experiments is is called Bonferroni correction. Okay, so let's see what we will get in this based on this Bonferroni correction. So P adjust p-values method equal to Bonferroni. Now this will be the corrected p-values. Let's call it P Bonferroni. So let's see what is the smallest one. So decreasing equals to true will give us the smallest p-value at the end. Okay, we cannot get all of them. Let's go for false here and get just one, the first one. So the smallest p-value that we got is 0.16. So this is a corrected p-value, and even the smallest one does not reject the null hypothesis because it is greater than 0.05. So we don't do any rejection here, and this is good because the null hypothesis is actually correct. Okay, but let's see now the following experiment. In the following experiment, what we have done is we have made a new data table, and this again has 5 people from the healthy population and 5 people from the diseased population. However, now the expression values for the healthy population come from a normal distribution with mean 100, and for the diseased population they come from a normal distribution with mean 120, which means that in reality the expression values in the healthy and in the mean population differ because they come from 2 distributions with different means. Okay, so I create the data matrix for the 5 first individuals. I create the data matrix for the disease individual here, and then I just merge them to make one data set. And again, I calculate the p-values for all of the 10,000 genes. And remember now that for all these genes, in reality the expression value is different. So the populations differ because they have different means. Now if we make the histogram, we will see that not all the picture here is quite different than when the null was correct. We have many genes with small p-values, and we have much fewer genes with high p-values. However, if we apply the Bonferroni correction here, setting as a threshold 0.05 divided by 10,000, then we just find 7 genes that are able to escape this threshold. Now if we do it with adjust, correct for the p-value, it will be the same results. Bonferroni is a method. And I try to find which of these corrected ones are smaller than 0.05. Then probably we'll see again the same 7 ones like before. Okay, now the problem is that in reality all of the 10,000 come from 2 populations with different means, but applying the test with the Bonferroni correction, we reject the null hypothesis only in 7 of them. So remember that we should have rejected the test for 10,000 of them, but we rejected it only for 7 of them. which means that we are super conservative. Being conservative means that we do not reject the null hypothesis as often as we should have rejected it. So we just rejected it 7 times. We should have done many more rejections. So the Bonferroni correction is ultra conservative. Now, if we see another plot, so I will do the following now. In order to explain what we usually do in biology, I will do this another plot. So first let's see that in the paper. Applying a t-test for each of the 10,000 experiments, this procedure results in 10,000 p-values. Now if I sort them from the smallest to the greatest, I will have p1, p2, etc., p10,000, where p1 is the smallest p-value, and p2 is the second smallest p-value. And so on and so forth, while this p1000 will be the greatest p-value. Now I will make a plot where here I will have the index. So the index here is 1, 2, 3 and so on. And here I will have the p-value. Okay, let's see how this will be. So sorted p-values will be sort p-values 2 and decreasing equals to false in order to have the smallest one in the beginning. Okay, and if I do the plot, so this will be 1, 2 length sorted p-values. This will be my x, and my y will be the sorted p-values. Then I have something like that, as you see here. I just I will put smaller points, so okay, and I will just focus on a small part of this plot, let's say from 0 to 0.1, because the scale is too large and we cannot see what's happening here. And so what I have done in R is that I have used the point 19. Point 19 means that the point here is a circle, but it's filled. So it's not a round circle like that as a point, but it's a circle like that. And I have made the original size of this circle much smaller, so 40% smaller. And then as a y-axis here, I use a smaller axis from 0 to 0.1. Okay, now if I have a significance cutoff value of 0 based on the Bonferroni correction, then this would be the following: AB line horizontal equals to 0.001 0.05 divided by 10,000, and the color will be red. Sorry, here the parameter is okay. Now if you see here that you cannot see that very clearly, but only these 7 points at the beginning have a p-value which is smaller than this line. So this line is the Bonferroni correction, and only seven points here in the very beginning are smaller than this line. Probably we cannot see that very clearly, but if we go to smaller value here, perhaps we will be able to see that. Yeah. So I just went to the very beginning here, and these values reject the null hypothesis. Okay, so let's go to the original scale, or at least to the 0.1 scale. Now you see that besides here the very beginning, nothing else is smaller than this threshold, which is a Bonferroni correction. What they propose in a different methodology, which is called FDR, is the following. Do not use a constant threshold like this one, but use a threshold that increases for p-values of different rank. So we will start from here, but then we will proceed like that as my pointer goes. So again, based on FDR, we sort the p-values, p1, p2, and so on until to p10,000. And the index of this p1 is 1, the index of this p2 is 2, the index of the pi is I, and the index of this p10,000 is 10,000. Again, these p-values are sorted from the smallest to greatest. And now we'll do the following thing. So in contrast to what we had before, where for all of them the threshold, so in Bonferroni the threshold for all of them, the threshold for all of them was 0.05, or in general alpha per experiment, divided by m. So the same for this one, the same for this one, and the same for this one. Graphically, this is equivalent to what we saw here, that for all of these p-values, the threshold is this red line. Now, instead of doing that, then the FDR suggests that the threshold will be this value multiplied by the index of the p-value. So this will be by 1, this by 2, this by I, and this by 10,000. Which means that for greater p-values in a single experiment, the threshold will be greater. So let's see that how it will go graphically. A B line alpha equals to, so the slope of this line will be will be 0.05 divided by 10,000, and B will be, so I made a mistake here. I should be, the slope it will be B, and it will be the 0.05 divided by 10,000, and the intercept will be 0. So this line is this green one. Now we reject the null hypothesis for all these experiments until the last one, so the one with the greatest index that fulfills the requirement that the p-value fulfills this requirement, that the p-value is smaller than the index of the p-value multiplied by the alpha by m. So this is 0.05, this is 10,000 in our experiment, and this is the index of the p-value. And we reject all the null hypotheses for all the indexes until the greatest one that fulfills this requirement. Perhaps in Wikipedia this is more clear. Let's go to FDR Wikipedia. I think it has a better plot. False discovery. FDR stands for false discovery rate. Okay, so again we reject for all cases where this holds, and actually we reject for all cases until the largest k. We had I in our experiment that this holds. So for example, this will be more clear here. So these p-values are smaller than the threshold, so correctly we reject it, but then this one is a bit greater than the threshold, and then we continue up to this point, and now all these green values are greatest from the threshold, so the greatest k that this requirement is fulfilled is this one. So all of them reject the null hypothesis, even though there are some here that do not reject the null hypothesis. Okay, so for all of them we reject the null hypothesis. Now in our plot, all of these guys here reject the null hypothesis, so we see that this should be something like 6.5 to 7,000 genes reject the null hypothesis. Remember that in this example, all of the genes actually come from different populations. So sick and disease people have different means, so ideally we should reject the null hypothesis for all of them, but at least here, as far as I see, we reject the null hypothesis for about 6.5 thousand genes. So let's see that. In order to do that, we will apply the p-adjust again for the p-values, but the method will not be the Bonferroni any longer, but it will be the BH. From the authors, the developers of these methods, it's two guys, Benjamin Hochberg correction, or else FDR. it will be the same in R. So using FDR, we correct the p-values, and let's see how many of them are smaller than 0.05 when we do the correction. Oh, FDR with small letters, sorry. Here it should be FDR. 6,855 genes, all these genes here. So for all these genes, we reject the null hypothesis. And usually, FDR is the methodology that we apply for biological data.